Those who don't know me, I recently transitioned from University of Leeds to back to Illinois Institute of Technology in Chicago, and my training has been in XTAFs. I graduated from Bruce Bunker Group at University of Notre Dame, but then, as most of us synchrotron scientists do, I broadened myself into many different techniques. And yes, today, as Jerry mentioned, I'm going to talk about a number of techniques and how their applications in a subject area, which I sort of started rather recently, like maybe about 5 years ago when I went to Leeds. Before that, I was mostly working in biogeochemistry, and I'm applying all those techniques and principles of biogeochemistry and synchrotron techniques into design of materials for sustainable systems. So that's why I chose the title Materials Challenge of 21st Century and How Can Synchrotron Help? So the outline of my talk is such that I actually will first talk about net zero and the materials emission challenge, as in to pose the context in which I'm solving these problems, and then very briefly that how synchrotron can help. The best way to showcase that is via examples, and I have chosen a few examples to show you, and each of them emphasized on one or two, a combination of techniques, and finally a summary slide. So bulk of the talk will be on these examples, like 2/3 of the talk is examples actually. So, and I'll have breaks as Jerry says in between for questions. So first of all, what I call the materials challenge of 21st century, and it's not just me, but has emerged as a big challenge, is basically the fact that net zero is something has become a very trendy word, and not just people, but nations, countries, national, like international leaders are chasing that with a target of 2050 and so on. But what does net zero mean? Net zero means reducing greenhouse gas emissions to ensure that any ongoing emissions are balanced by removals. So there are two things. One is that we have to reduce emissions, and also we have to balance that by removals. Now, in this context, the good news is that global transition to more sustainable and circular economy has happened a lot faster than was previously imagined. Like maybe 20 years ago, nobody was thinking about it. But most of the transition is happening in the green energy space. And however, developing green energy is not enough because, as you see in this slide on the left, on the right, sorry, is that the global emission actually only about half comes from the energy sector and about 45% come from the product sector, as in materials. Product is what designing or manufacturing materials. So then the thing is that unless you have unless we also tackle the problems, materials problem very well, we cannot, even if we do very good job, even if we do a stellar job achieving complete green energy, it will still only solve half of the problem. The rest half will remain unsolved. And that's why designing economically and sustainable carbon negative materials is important to overcome this materials challenge and to actually achieve a truly circular bioeconomy, achieve net zero, and so on. Fortunately, though, transformation of biomass waste residues has emerged as a very potent method and viable pathway for this kind of work, for designing new materials. So when we think about designing high performance carbon materials, we of course think of things like fullerene, carbon nanotubes, graphene, and so on. These are all very high performance materials gone on to win Nobel Prizes. But the way they're produced is very different today. What the question is, what if we can produce that using biomass waste? So that's what some of our research has been dedicated over the last few years. Is the main goal of these research efforts is rational design of bio-waste derived high value products for tailored applications. And those biomass could be, or biomass derived waste could come from anywhere, like urban waste, municipal solid waste, sewage, agricultural residues, forestry, and so on. Our research is more focused on agricultural waste residues at this point. So next, the connection, I mean, because I'm born and bred into a synchrotron community, so what is the relevance of synchrotron here? Now, I think that synchrotron has a central role to play in these kind of all different techniques that we have in hand. So is this also appearing on your screen, or can people see the screen quite well? I don't know how to put this off. Uh,
It's fine.
okay, all right. So we start with these kind of waste residues, and then we carbonize that material through different processes that I'll show you in a minute. And then we have different kind of chemistries that goes on. And so there is no other method as good or as powerful to understand what is going on during the carbonation process and how we tune the material for different applications, as well as how can we functionalize them after we have already produced the carbon material from the waste feedstocks. And here we can use either surface interface techniques such as NexAFS and XTEXM. We can use bulk techniques like XAFS, XAS, like both NexAFS and Zanes and XAFS, and XRS, X-ray Raman scattering, and finally micro tomography and SACs. Today I'll not be talking about SACs, but all other techniques. So now coming back to biomass to carbon materials, and to an extent bioenergy as well. So this field has been rapidly developing, and initially started with conventional biofuels, which was sort of competing with food materials. And so that was a big issue, because we also have hunger issues, poverty issues in the world, and that needs to be solved as well. So we cannot be solving our energy and material issues at the cost of hunger issues. So fortunately, the field has evolved very rapidly, and now this second and third generation of this research is talking mostly about bio-waste residues, and these residues can be, you know, things that are actually considered a waste in the agricultural feedland, and using those to do many different kinds of thermochemical, biochemical, and hydrochemical conversions to produce what we call either pyrolysis carbon or hydrothermal carbon. I mean, we can do different kind of things, and some of these are actually, again, related to energy, and some of these are related to materials. So pyrolysis and hydrothermal carbon are actually two potent carbon materials. The way pyrolysis is done is that you take carbon feedstock and heat it into a very high temperature or higher temperature that could range anywhere from 400 degrees to 800 degrees Celsius under inert atmosphere. And what you do in that process is that you do thermochemical breakdown of that material. And there are many different drivers, as in not only the temperature, but you can do fast pyrolysis or slow pyrolysis, and you can rate of pyrolysis and so on. Everything makes a difference, and in the feedstock, and also the starting feedstock makes a big difference as well, as we'll see in some of the slides later on. And even more sustainable, another method that is even more sustainable is hydrothermal carbon, in which we actually take this the same kind of feedstocks and put them suspend them in water, and take the temperatures only to 200 to 250 degrees Celsius, and this is called hydrothermal conversion. They both have different advantages, and one of the advantage of the pyrolysis carbon is that it actually has strong structural integrity, but it is not always as well functionalized as one would want it to be. On the other hand, the HTC material, that is hydrothermal carbon, is highly functional, but it does not has as strong structural integrity. So sustainable carbon materials of the future should combine the structural stability of pyrolysis carbon and the surface functionalization of hydrothermal carbon. And if we can achieve that, then we have a stellar kind of material going forward. So that is one thing, that we can produce this material that has already been done. So what more? I mean, of course, we are always striving to do better. And one thing that we can actually do as a community is to enhance the physical and chemical properties of these carbonized biowaste for high performance. And that's the area where we try to specialize. And that can be done in three ways, basically: physical, chemical, and biological. I'm not going to talk about the biological amendment today, because that is something that we do only in collaboration. That's not something that we drive ourselves, but we do physical and chemical amendment. So the way we can change physical properties is by tuning the porosity. Of course, surface area as well, but porosity is a very powerful way of tuning the physical properties, which includes size exclusion for ions and selective size exclusions as well. And then in case of chemical properties, we can do ion selective chelation, and we can impart redox capabilities for oxidative or reductive transformations. So here I show you that one of my favorite feedstock is actually this spent coffee grounds. Who doesn't love coffee? And this is also the reason it is my favorite is not because most people love coffee, but also because it's a very, very good material in terms of it's a software material. It has a lot of protein residues, so it is highly functionalized, and hence that can be tuned for many different purposes. So you can start with this, and then you can dope heteroatoms like nitrogen and sulfur, for example, to make hydrothermal carbons. This is how they look, beautiful spheres. And then you can actually functionalize nanomaterials by calcining them or pyrolyzing them. You can also directly pyrolyze this material, of course. In the process, you can tune porosity either this way or straight. And then finally, products that we have produced in our own lab as cross-linked hydrogel beads or functionalized nanocomposites. So if there's any question, I can have a quick stop here. Otherwise, I'm now going to go into giving some examples.
I think we're good. You should continue. It's a terrific start. Thank you.
Okay, perfect. Thanks, Jerry. So first, I'll give you an example using scanning transmission X-ray microscopy. And I must, while I'm talking here, I must give due regard and recognition to people who have actually done the work. And Luke was my first PhD student, but also continued as a postdoc in our group. And he has done the extrixum and XRS work that I'll be showing today. So for those who might not know so much about scanning transmission X-ray microscopy, it is a wonderful technique if applied properly, because what it does raster scanning. But while doing the raster scanning, it actually also takes a snapshot at every single energy point. So while it's raster scanning in XY, it also is scanning in energy. And so we have a stack scan, energy stack scans, such that we also have the full picture of the whole thing with a very high spatial resolution of the order of 20 nanometer, if you want, of the area for the region of interest. So basically, it does not only produce pretty pictures, it also gives full chemical information in addition to give full or a very high spatial resolution. So we use this method to try to resolve a long-standing problem in the carbon community, and that was the hydrothermal carbon. It was long thought that these hydrothermal carbons, which as you show is growing here from a small size to larger size as temperature grows, is that they might have actually core and shell structure. So we collected one of these, and then we actually did fifth sectioning and took to diamond for extrixum analysis. And this is the reason you can see this is the cluster analysis of that. And what we came up with is this beautiful core shell image. And if you do extract the spectra from that, this is what you have. Of course, one might say, oh, this is relatively small differences. Of course, in a material which is mostly like 90% carbon, you can't really expect huge differences. But all these differences actually account for some important transitions, as you can see here. More importantly, when we actually took the core and shell regions and extracted spectra out of that and analyzed those, we found that what we have is a beautiful picture. That interpretation that came out in nutshell is that aliphatic and carboxyl linking units join polyfuranic domains at the surface, as you can see here. And then, but in the core, linking units are removed, leaving condensed polyfuranic domains. So basically, I mean, in nutshell, Yes, it has a distinct core versus shell, and the core is different. Although the carbon, nitrogen, oxygen ratios are very similar, and that is why this people had failed to understand the difference between core and shell using things like XPS and other things, because the empirical ratios remain the same. The way they bond and the way the carbon moieties are formed is different on core versus shell, and that was a very big deal in this because hydrothermal carbon are used as capacitors or can be used as capacitors. It has already been shown that they can be, and so tuning the surface properties is very important. So in this paradigm, there's actually something else that also was very cool that we were able to do. We were fortunate to be invited to help a group at Imperial College London, who was trying to develop low-cost carbon electrocatalyst for oxygen reduction reaction. And this is an area that has also been very prominent recently, because it has been found that dispersed iron nitrogen doped carbon catalysts have emerged as a promising alternative to costly platinum-based counterparts in fuel cells. So what they did is that they started with HTC. They started with actually sugars, and then they doped nitrogen during the formation of HTC. Then they put iron into that system as an iron chloride, and then they pyrolyzed that, and they form beautiful this uh, FEN, FEC kind of products, and then they etched that with some acid bath, and what they had ultimately is beautiful FEN4 kind of material, which we helped them showcase. And this high purity FEN4 materials, FEN structure is very good for oxygen reduction reaction. And this is just a schematic that I show that this has multiple applications. This kind of technique has very good applications. And also this was the first time, although this was not the first time that it was shown that FEN4 can do very good ORR reaction. But this was the first time that one started with rather cheap and I mean low cost, but yet scalable material and achieve that. So these were some of the applications for HTC. And now, again, Jerry, if there is any question, I can stop here before I move on to my next set of slides.
I think you're good for the moment.
Okay, perfect. So one can really not study carbon these days without invoking some extra-Raman scattering. And I'm sure Jerry is laughing, smiling at that, because he has been a big promoter of this, and he has worked very hard in this area. So I'm not going to give much detail about what extra-Raman scattering is. This whole XAFS Journal Club was started with a beautiful talk by Jerry in March of 2020 on extra-Raman scattering, and that was followed up by Simo Hotari, who is one of the stalwarts in the field, and the second talk was also on extra-Raman scattering. So I'd rather ask people to go and look into those talks if they want to know a bit more. But I'll give a very quick refresher of what extra-Raman scattering is. This is basically a new application of an old technique. The technique is not new as such, but fortunately, the advent of high flux photon sources actually has made it possible recently. So what you do in this case is that instead of trying to, and in the context of carbon, instead of trying to shine 280 electron volts on carbon, what you do is that you go to 10 kilo electron volts, and then you shine the X-rays on these carbon materials, which get scattered and goes to crystallizers, and then ultimately the monochromatic beam goes to detectors. And what you plot is basically energy loss spectrum. And this energy loss spectrum is very similar to what you would have for NextSAFs. And again, this is how the schematic works. And in the approximation of low Q, as in low momentum transfer, what you have is that you get the same information that you'd get for NextSAFs. Now, why only low Q? I mean, because you can use actually dipole approximation in low Q. However, this technique is not limited to low Q. You can also go to high Qs, and you get a lot of other information there as well. However, for our purposes, we have limited ourselves mostly to low Q, because what we are really interested in trying to get the same information, basically, that NextApps can give us, but not just from the surface. So we want to be bulk sensitive, because we are trying to develop a lot of materials, which it is very important for us to understand the bulk properties. Why I'm emphasizing about bulk? Because in case of carbon, you have 3 orders of magnitude higher penetration depth for carbon using 10 keV, instead of using the carbon KH of 280 to 300 electron volts. So that's what we have done. We have used this technique successfully at ESRF and APS. There are many different places that you can use. Fortunately, there is also, I'm part of a committee which put forward, a panel which put forward this kind of beamline at Diamond, which has now been approved. So there's one that will be built at Diamond as well. So, but meanwhile, let me show you that when we used this extra scattering to try to understand the difference between these two kind of materials, biochar versus hydrochar, of course, we saw tremendous differences, because the way they're made is very different. So what you have is that you have different kind of transitions that we analyzed. And in nutshell, I can tell you that basically what you have is that you have very high aromatic component for the biochar, and hydrochar is very different, which has much more carboxyl carbonyl kind of component in it. There are many other differences, of course, and those differences can also be tuned based on, or enhanced or accentuated based on the process conditions that you're working with. So one way is to understand that the difference in biochar and hydrochar, not just on the surface but overall bulk, but also to be, we also went ahead and looked those on surface versus the bulk, which I'll show you in a minute. But first, understanding the process conditions. So here is something that you see that oak pyrolyzed at 450 degrees Celsius and versus 650 degrees Celsius, and you do see that there are differences. A, you see that there is at 650 you have more graphitic component here, this resonance, and also B, you see that the broadening of this peak at 650 compared to 450, and this relates to basically the carbon backbone that you have. We also conducted X-Raman on HTC material, and don't ask me this. This is a DFT calculation that was done by our very good collaborator Christoph Saleh, and he helped us understand the basically, just like the way you understand Zanes, this is what we were trying to understand X-Raman, and that is very useful in terms of now, DFT, in my opinion, has not reached a stage where we can fully produce the entire spectrum, but at least we got, Christoph was able to get very good measurements in terms of matching the energies for different peaks. So we know that what different peaks are. And I mean, as a community, we all would, and I definitely would like to see more and more integration of these theory and experimental, newly designed, developed experimental techniques to get better understanding. So, now, we have understood the difference in these two kind of basic carbon materials. We have also understood the different process conditions, although there is so much more to understand. Now, we can also try to understand this bulk versus surface carbon chemistry. And so we use soft and hard X-rays. And in this case, we use NextApps to try to understand what's happening on the surface. In this case, I mean, the advantage of NextApps include that it has very large signal, relatively easier to make measurements. However, XRS also gives some very important advantages, such as that it is saturation free, and it can do bulk measurements, and also it can be performed in complex environments, sample environments, so to say. So ideally, one can imagine that for many systems, one should get the same kind of spectrum, whether using NextApps or XRS, which any user which has actually used these would immediately say, no, that's not going to be the case, and rightly so, because actually there are differences between the two, and you'll see that right away. So here is hydrothermal carbon measured using XRS, and the exact same sample measured using NextSAFs. So you see that there's a huge difference in the peak here, which we're still trying to make sense. But this was not a mistake. This was not something because we repeated these measurements and we actually even know that what kind of peaks are these. So these measurements tell us that actually the surface is very different from the bulk, sort of corroborating our some earlier experiments as well. And this is not only limited to hydrothermal carbon, also in pyrolysis carbon, we found that when we did use the exact same material to do our NextSAFs versus XRS studies, we found that there's systematic changes as a function of temperature. Here's 650 versus 450, and here is HTC material at 250, for example. So again, I mean, what these tell us, what these properties tell us, these differences tell us that how we can actually use these materials for designing for desired properties and tailored applications. So next thing I'm going to talk about is tuning porosity. But again, Jerry, should I stop?
Well, there's two questions, and I'll urge people to add their questions into the chat also. First question is, thus far in talking about the biochars, you've mostly talked about catalysis and related applications, but one of the big fields in biochars right now is soil amendment. And I was curious if this finding of yours about the difference between the bulk and the interior had some role in understanding either how to improve biochar or the role of biochar as a soil amendment.
So Jerry, this is a wonderful question. And there is a very conscious effort from my part that I was trying to get away and not indulge into soil amendment aspect. but there you are. So there's a lot of work that is being done in soil amendment aspects of it. And that is something that we are also working on, but we are working on via microbial amendment of biochar. Because see, just adding biochar to soil is also very useful because it is a carbon negative material. It absorbs CO2 from atmosphere to the soil and hence locking CO2 in the soil in the longer term. It also helps regenerate soil carbon organic matter. That's fantastic. However, biochar can also be somewhat of an inert material, which is not entirely true because it also does a lot of ion exchange. The results that have been shown by just adding biochar have been mixed at best. Now, to go on to the next generation of biochars, which actually show very potent applications, and we have done some pilot work on that, and that is in collaboration with the microbiologist, is to actually use microbial consortium to unleash the nitrogen and phosphorus locked in biochars and hence increase the soil productivity and soil fertility. In terms of structural, that is a project that could be my dream project, which I actually wrote an application for one time, has not been funded yet, is to how to understand how to make sure that there's a released control of these nutrients from biochar into the soil. Now, the research that has been done so far is actually mostly that biochar was added and we saw this kind of enhancement. And there is a high regard. I mean, I have high regard for that, but that's sort of not what I am into. And I want to see some more nuanced kind of applications where there is a direct benefit that is well controlled. I don't know if I answered your question or went in a tangent.
No, certainly. I was just curious about structure property relations, but it seems, but I think you're right that the overwhelming amount of work on soil amendment has been, shall we say, phenomenological rather than microscopic thus far. Okay.
Yeah, because if you go to a biochar conference, which I have been to a few times, the people you meet are very well regarded, of course, but less than half the community is a scientific community.
Mhm.
And I'd like to see a bit more of scientific infusion into that community, but it's still it's a very potent field. But also actually there are a lot of other applications that are coming up, including different kind of fillers, tire fillers, and different kind of paints, coatings, and so on. So there's a lot of different applications that are happening more
Okay.
recently.
There's a second question. If you can go back to, I think it's the last slide where you have the pyrolysis carbon, that one. Why is the why are the spectra so dissimilar at, say, 2995, 2996?
2990.
The big
okay.
the big
Oh,
bump.
yes, here.
Yeah.
Yeah. Okay. So this is actually graphitic resonance. That is can be seen very clearly in XRS, but not so much in XAFs, and that clearly tells us that basically this thing. And you see that this is more pronounced at 650 than 450, and that is because as you go higher and higher temperature, the pyrolysis carbon or biochar becomes more and more graphitic in nature.
More and more graphitic. Okay.
Yes. And while that's not happening on the surface at all. So initially we were not sure if our spectra actually makes sense, but there are a lot of systematic changes. As you can see at 450, the aromatic component on the surface and bulk is roughly the same. But that starts decreasing at higher temperature. Also, but at HTC, you see that on the surface, actually, there's much more aromatic component than in the bulk. And a bit of this is actually also related to background, the way background is removed and so on. Is my best guess, but here the way you see these, I mean, here it's mostly background, Jerry. If you,
Okay.
I mean, you probably know better.
All right, so it's something systematic down there, but up top when you
But
actually
here,
have the
yes.
graphite peak.
Exactly.
Okay,
exactly.
I
You see
understand.
the peak is here, and that is even more enhanced here.
Okay. Not seeing any additional questions. You should continue, please.
Perfect. So next, I was talking about tuning porosity as a physical method, and this kind of work has also gained a lot of momentum recently. That how can we develop not just tune porosity, but develop hierarchical pore structures within carbon materials, because carbon materials are considered porous materials, perfectly fine, wonderful, but they have already an inherent porous structure. Now, if only we could impose a hierarchical pore structure such that we have macropores, and within those macropores we have mesopores and micropores, we can have very strong active sites. And not only that, what we can also have is that we can have a very controlled diffusion if you want, or other kind of flow properties. So basically combining a network of macro, meso, and micropore enhances functionality because it facilitates more efficient transfer to and from active sites, and also increases the degree of pore size control for ion selective absorption. And this is just, these are our own images. You start from biomass and you have this biochar. And in this next slide, I want to show that we have taken 3 different feedstocks: rice husk, oak wood, and spent coffee beans. So oak wood was a clean material, rice husk was a pure waste, and spent coffee beans was also a pure waste. But rice husk is a much harder kind of material, because it has a lot of silica in it, and spent coffee beans is much softer material. So these were the reason for choosing them. Of course, one can choose anything one wants. So this is the biomass, and tomography was done on these just pure biomasses without any carbonization first, and you see that they have lower macroporosity. Of course, when you're using microtomography, we are not actually measuring microporosity, we're measuring macroporosity, because the resolution that we used was more like in the order of 0.1 to 0.3 microns. And then you make biochar out of those, and then you have like a very different kind of macroporosity. Further, one can activate using different techniques. One is acid activation, base activation, also zinc chloride activation. And the idea is that you can use different kind of chemical activations to try to create different kind of pore structure. And that's a very powerful thought, because also one thing one would want, if one wants to use this for consistent product formation or manufacturing, then they have to have like very simple pore structures and so on. So here is, I hope this works. Wait a second. Oh my God, what's happening? Do you know of this problem that sometimes don't work? Yeah, okay. Fortunately, it does. Okay. Wait a second. Can you see the
That's
video?
good. Yeah, that's good.
Okay, thanks. I was wondering if it'll work or not. So this is actually the whole, I'll quickly run one more time. This is the whole, so raw biochar, ochre, HNO3, manganese, and zinc doped. And then you see that how the bulk is. But then also what I wanted to show is that you can actually go and so this work is led by Stella Foster, a PhD student, and she has done this beautiful work where it's not just about, you know, tomography doesn't have to be about pretty pictures, as you already saw in the last figure, that and this figure actually, as people would recognize. 1 second. Oops. Looks like I can't go back. Yeah, this yeah, this is a lot of work, as one can imagine, that this is actually extracting the pore volumes and so on. So this is computationally heavy work, and this simple image is deceptively simple in a way. But more importantly, she has also done some tortuosity work, where, and for those who might not be aware of this term, tortuosity refers to the ratio of diffusivity in the free space to diffusivity in porous medium. So if you want to use these materials for diffusing something, be it gas, or which is very important for catalysis, or even for water purification or other purposes, then one has to understand that what's the isotropy. Are these materials isotropic, first of all? Is the flow same in all the three planes? And number two, that I mean, how does it refer to is as if there was no medium or something? So again, looks like I'll have to do some dirty dance here. What is going on? Okay, yeah. So this is, we see in X, Y, and Z plane. Okay. So this is XY plane, YZ plane, and ZX plane. And this clearly shows that they're not completely isotropic. So there's anisotropy in these materials. And that can either be a challenge for certain applications, or that can also be a wonderful thing for some other applications like you have. So basically what this means is that you are going to have a preferred orientation in which the flow will be faster compared to others. So, okay, no, let me, yes, okay, all right. So next example I want to give is designing manganese oxide biochar nanocomposites. And manganese oxide biochar composites is actually, again, very, say, has emerged as a very important class of materials, I would say, because there's many different ways you can create manganese oxide biochars. And the applications are wide-ranging, starting from high value absorption or advanced sorbents, but also catalysis, particularly oxidative transformations, because manganese oxides are known to be strong oxidants, and also capacitors. So we started with 3 different kind of treatments. We started with biochar, and we soaked them with manganese chloride, which is highly soluble, manganese 2. And then there are 3 different treatments that, and this work is led by Flora Brogza, who is also a PhD student. So she did different kind of treatments, and the results were very different. As you can see that this is manganese standards, Zanes, And we saw that treatment 1, you can see, gives very different kind of spectrum compared to treatment 2. And comparing this, you can see that treatment 2 actually has a lot more manganese 4. And that was indeed the case. We saw that treatment 2 had mostly manganese 2 and manganese 3, while treatment 2 and 3 had mostly manganese 4. So once we realized that, we actually also went ahead and tried to understand that what was happening in terms of different species of manganese 4. And so we did a full-blown analysis, and we found that, well, treatment 2 and treatment 3, and these are different. So OCUD 450, OCUD 650, RICES 450. So we're using different kind of OCUD and RICES to try to understand.
Did I freeze or did Bhoopesh freeze?
I think Bhoopesh froze.
Okay, well, we'll, and he won't know we've had this problem before. I will ping him with an email just in case, but he may not see that. Hopefully, he'll realize there's a problem and perhaps jump out and jump back. If anyone has his phone, please text him, and I think I might have it, and I'll try to do that too. Okay, presumably he'll be back in a minute, and I'll be able to trim this out of the recording.
Hi, Jerry. I'm back. I don't know why my laptop suddenly died. Fortunately, that's an older one. Let me quickly try to transfer my stuff from the old one. 1 second. I think I also, really sorry about that, but if there are any questions, meanwhile, I can. Okay, let me download this here.
Just focus on the slides. We'll hold the questions.
Okay. All right. Okay.
Thank you, everyone, for your patience.
Second. The problem is that my slides are on the other one, so let me transfer. Oh. Okay. Shutting that up. Just starting that. Okay, I'm restarting my older laptop to at least transfer the material. Okay, I unfortunately saved on a Google Drive, so that is downloading now. So that's good because okay, all good. I would need to share screen.
And
Thank you everyone so much.
You were on the
Sorry.
slide where you were talking about the
Yes.
manganese oxidation state.
Exactly.
Okay.
Thank you so much everyone for your patience. Is it full screen or is it behaving?
No, right now we're seeing your slide view. So you may need to unshare and then share again, for example. We're not seeing the projected view.
Okay, so that is because actually I might have.
All right, we're still seeing your slide view rather than the projection.
Yeah, 1 second. Duplicate this. Do you see the full view now?
Sorry, no. Again, if you unshare, then usually you can choose. There it is. You've got it now. We're good. All right. That was good. Now we're back at the slide view again.
Okay. Okay. So that will be good again. Is it or not yet?
Not as yet, but we'll give it just there. Okay. You're not sharing.
I'm not sharing, and I'm going to share again.
Very good. All right. You should choose a way to continue on this slide, and it'll be great.
Okay.
Thank you.
Okay. All right. Thank you so much, and really sorry for this technical difficulty. So we were actually it might have some differences, but anyway, so I was saying that there's we tried to design magnesium oxide biochar nanocomposites, and we started with manganese. We started with biochar, and then we soaked manganese chloride to it, and which is manganese 2, and then we did Zane's analysis to see, of course, after paralyzing it, we tried to see that what was happening with the manganese oxides. Is it forming manganese oxide biochar or not? It was not as straightforward as we thought it might be. So what we had is we had for manganese treatment 1, and treatment 1 was mostly manganese 2 and 3. But treatment 3 and 4, treatment 2 and 3 led to mostly manganese 4, as you can see. And then we went to do a full-blown analysis to understand that what was happening in the overall manganese, not just oxidation states, but what kind of phases of manganese were those. And we saw here that, as you can see, that basically we had all kind of different species of manganese. So we were like, okay, great. I mean, at least we have manganese 4 oxide, which can, and particularly if you look at OCOD 650, we had MnO2, we had triclinic bernicite. And so that was very encouraging that, okay, that could be a really good one. So now, as you know, that calcination is a holy step that most of us want to do for making good catalyst. We tried to we did calcine this material. And what we saw was kind of pretty interesting and remarkable in its own way. So what we saw is that when we calcine, so the calcined material is in dotted lines and non-calcined material is in solid lines. So you consistently see that the calcined material, and of course this line represents manganese 2, and the green represents manganese 3, and this magenta represents manganese 4, is that there's a reduction of manganese during the calcination step. So instead of getting much better and well-formed catalysts, we actually went the other way around. And then it occurred to us that, okay, I mean, this we should have known from the get-go, that these biochars are actually not inert material. They have a lot of carbon moieties like quinones, which are electron shuttles. They also have reduced sulfur groups, which we know because we have measured those, and I'll show you in one of the next slides. And in addition to those, we definitely also have iron oxides embedded in it, mixed iron oxides. So they can be quite a strong reductant, and when you heat them up in the calcination step, these electron shuttles actually become more active. And so instead of forming better better catalyst, they went to make it a much more poorer catalyst. So that was just an interesting aspect that they wanted to emphasize on as well, that when you're dealing with these kind of materials, then the conventional wisdom might not always apply. So next, we actually we're finally able to get good high performance manganese oxide biochar nano composites with superior performance. That was OCOD 650, and we also did high resolution TEM, and we were able to do this. We were able to do lattice fringes on these, and finally, but also, and a special mention to Shani Jha, who actually was a high school student at that time, and she contributed to this part of the project. And she was also a winner of a Stockholm Water Junior Prize. And she was able to show that this material can have very high metal removal, heavy metals that includes cadmium and lead and mercury and arsenic and so on, and also pretty high microplastic and pesticide removal. The antibiotics removal was not that high, but nonetheless, I mean, it was not too bad either. So this is something that was there was quite a learning that happened in this process. And again, there are many different ways this can be done, but this is an example of how one can combine advanced absorption properties as well as catalytic properties in these materials, and as carbon-based catalysts and carbon-based nanocomposites are very, very good ways to proceed forward. So the next and the last example that I want to give is actually of how biochar can also be a natural sorbent as well as a reductant. So in this case, this was really the fun example, and I wanted to end with this because in this case, what we had is that we thought of removal of gold, aqueous gold from industrial wastewater. And so first of all, we were able to show that biochar has very high, and this was oak wood biochar, has very high gold uptake capacity. As you can see, that in terms of milligram per gram, it can go on to very high levels. And then we were able to use TEM and also diffraction analysis to show that indeed gold clusters were formed on the biochar. And the way we tried to rational these is we did sulfur and iron zanes on these materials, and we found that most of the sulfur budget is actually in the form of, this is the sample, this was in the form of reduced sulfur groups like cysteine and methionine and so on, which actually are known to reduce things. But also, more importantly, it had mixed iron 2 iron 3 oxides, more like magnetite, which is a very potent reductant, of course, and that reduced gold. Gold can be reduced relatively easily. That's a known thing. We further conducted XAPS analyses to show that basically there was a difference in the first and second shell, and then the size of these particles were constantly getting smaller. So we also did some yields analysis to actually show that what we have here is, you can see that the position adjacent to these gold clusters had a higher percent of iron 3, and closer to this, distant to these was higher iron 2. So again, I mean, nearby was more iron 3, and close by was more iron 2. So this was a smoking gun. This was a smoking gun, proof that actually this iron oxides are responsible for this kind of reduction of gold 3 into gold 0. And also, XAPS shows that the particle size, basically, as we go further, the particle size decreases. So as we go higher loading, particle size decreases. How can we make a rational of that? So the thing is that initially, it turns out that these iron 2,3 mixed iron 2,3 oxides are the active sites, and they form rather large gold clusters on the surfaces. As the loading of gold increases on this biochar, then what happens is that these relatively less potent reductants like quinones or reduced sulfur groups, they actually reduced gold in more like in monatomic form of gold, and that is embedded in the mesh of this biochar carbon. And hence, we came up with a threshold at which, in terms of milligram per gram, of the gold versus gold is to biochar, which will be very economically useful, and which will be very economic in terms of recovery of gold from wastewater. And why wastewater? Because there's a lot of e-waste that is happening these days, and then there is gold circuits, printed gold circuits in them, which can be recovered this way. And that is shown in the schematic here. And also, using microtomography, we show that the larger gold clusters are indeed on the surface. So that's sort of what all I wanted to talk today. And at the end, all I'll say is that what I have demonstrated is that there are many different applications of synchrotron for rational design of sustainable carbon materials. And one can start with these lignocellulosic biowaste, such as rice husk or spent coffee beans. One can go to dope heteroatoms in hydrothermal carbon, which I've shown can be used for oxygen reduction reactions. Further, one can functionalize nanomaterials and form nanocomposites. One example that I skipped today, did not give, was also cross-linked hydrogel beads that we have developed. And in all these processes, what you see is that for in situ formation mechanism, XRS and SACs can be used. For nucleation sites, 6-7 and XAPS can be used. And of course, tomography, as you have shown you examples for tuning porosity, XAPS, operando XAPS is super important for these. So there are many different XAPS, not XAPS, but synchrotron techniques, including XAPS, that can be used to for rational design of these materials. And with that, thank you very much. And I must also thank especially to Beamline personnel, without whom this work would not have been possible. Most important, Christoph Saleh from SRF, and Burkhard and Sashi from Diamond, and Mali, Matt Newell, and Tony Longiorati from APS, and all the funding agencies that was actually majority of this work was funded in the UK by EPSRC, Royal Society of Chemistry, and also Science and Technology Council. And again, if you have questions, you can also email me later, or you can just ask me about all the why, what, why, and where right now. Thank you very much.
It's a terrific talk, Bhoopesh. Thank you. While people are typing in their questions, and we'll go a few minutes over. Oh, you should leave your slides up. You should leave your slides up.
Okay.
We'll go a few minutes over to allow questions. I'll start with a question. You talked about the manganese oxide nanoparticle composite with the biochar, and I didn't follow what the application was. Maybe you can go back to that and help me there.
Sure. So, okay. There are many different applications. So the reason that we were trying to develop this initially, and still that is one thing, is that, so this is, we have developed thiol modified, thiol as in SH groups modified, MnOx, mostly manganese 4 biochar. So what we are then doing is that this was for mercury capture and oxidative transformation of mercury. So from flue gases or whatever else. But turns out that this is also a very good material for water purification. So this result that I'm showing here on the right top is basically for water purification.
Sorry, I don't think we're seeing the same slide as you. We're seeing your slide view, not your projected view, perhaps.
So what slide is
your last slide?
All we're seeing is your last slide. We're seeing your PowerPoint program, not your projected view.
Okay, so sorry about that.
It's okay.
Let me do one thing. Let me actually first close a number of slides that I have. That will probably make things easier. Okay, so now I have only one, so that should help. Here. Okay, and let me do this full screen. Okay, so which slide do you see now?
You know, we're seeing your slide view, but why don't you just go to your slide view that you need, and we'll just use the PowerPoint view. That's okay. All right, so we're seeing the slide high performance manganese oxide biochar, and we're seeing it in PowerPoint, which is just fine. So yeah, go ahead.
Yeah, so what I was saying is that the idea was to actually develop this for capturing mercury from effluent gases and flue gases and so on, because mercury is usually in mercury zero state. So the idea was that manganese oxides will oxidize mercury to manganese oxide, mercury oxide, and then if there are thiols embedded in this, functionalized in these jars, then we also know from my previous research that these mercury can then be converted into mercury sulfides, which is very stable. So that would be a very potent way to first capture mercury zero and then oxidatively transform that into mercury oxide, and then eventually convert them into more stable mercury sulfide or mercury thiol forms. So that was the initial intent, which we did succeed partially or to an extent. But more importantly, what also happened in the meantime is that we sort of, not completely accidentally, but because we want to test that anyway, but we also realized that this material is actually very good in water purification, because you see that it not only takes away a plethora of heavy metals, including cadmium, mercury, lead, and arsenic, but also does a very good job with microplastics. And that is likely because manganese oxides are also breaking down microplastics and pesticides. Not so well with antibiotics, but that's okay. It's still 50%.